Son un apoyo al equipo de sonido. Si nos pueden proporcionar también el segundo apuntador, quisiéramos tener los dos si es posible. Gracias. Solamente para apuntar. Gracias. Muy buenos días, tengan todos ustedes. A nombre del Departamento de Ingeniería Química del Centro Universitario de Ciencias Exactas e Ingenierías de la Universidad de Guadalajara y del comité organizador, tengo el honor de darles la bienvenida a la Cátedra Neal R. Amundson 2024, que en esta ocasión cuenta con la distinguida presencia de nuestro invitado de honor, el doctor Jean-Philippe Steyer, del Laboratorio de Biotecnología del Medio Ambiente, perteneciente al Instituto Nacional Francés de Investigaciones Agronómicas, LBE-INRAE, por sus siglas en francés. Muchas gracias a todos por su asistencia. Antes de continuar, me permito presentar a las distinguidas autoridades que nos acompañan en el presidium. El doctor Humberto Gutiérrez Pulido, en representación de nuestro rector del CUSEI. Le damos un fuerte aplauso, por favor. El doctor César Octavio Monzón, director de la División de Ingeniería del CUSEI. El doctor Martín Arellano Martínez, jefe del Departamento de Ingeniería Química. El doctor Norberto Casilla Santana, coordinador de la Cátedra Amundson. Y nuestro invitado especial, el doctor Jean-Philippe Steyer, del Laboratorio de Biotecnología del Medio Ambiente del Instituto Nacional de Investigaciones Agronómicas de Francia. Contamos también con la presencia del ingeniero Antonio Rodríguez, fundador de la Cátedra Amundson. A continuación, cederé la palabra al doctor Norberto Casilla Santana, quien nos va a dar una breve semblanza de la Cátedra Neal R. Amundson.
Buenos días a todos y todas. Doctor Humberto Gutiérrez Pulido, secretario académico del CUSEI, con la representación de nuestro señor rector, doctor Marco Antonio Pérez Cisneros, doctor César Octavio Monzón, director de la División de Ingenierías del CUSEI, doctor Martín Rigoberto Arellano Martínez, jefe del Departamento de Ingeniería Química de la Universidad de Guadalajara, nuestro distinguido conferencista magistral, profesor Jean-Philippe Steyer, colegas, profesores, estudiantes, amigos que nos acompañan, todos reciban un cordial saludo. Asimismo, saludo efusivamente al profesor emérito de la Universidad de Guadalajara y querido maestro, fundador de la Cátedra Neal R. Amundson, en conjunto con el profesor Jorge Emilio Puig Arévalo, para los que solicito un fuerte aplauso y que nos pongamos de pie para ovacionarlo en este 25 aniversario de la cátedra. Gracias, pueden tomar asiento. La cátedra Neal R. Amundson es un evento insignia del Departamento de Ingeniería Química de la Universidad de Guadalajara y representa la cátedra con mayor tradición científica en nuestra casa de estudios. Lleva con orgullo el nombre de Neal R. Amundson, considerado el padre de la ingeniería química moderna. Desde su creación, la cátedra Neal R. Amundson ha tenido como objetivos el de promover el desarrollo de la ingeniería química en todas sus áreas, así como fortalecer los lazos de colaboración y amistad con instituciones de educación superior a nivel global. Este año celebramos con orgullo el 25º aniversario de su fundación, un logro que fue posible gracias a la visión del maestro en ciencias emérito Antonio Rodríguez Sánchez y el doctor Jorge Emilio Puig Arévalo, quienes, con el respaldo del propio profesor Neal Amundson, dieron inicio a esta noble iniciativa. En estos 25 años de historia, 38 destacados científicos e ingenieros químicos de disciplinas afines han honrado esta cátedra con su participación, entre ellos un premio Nobel. Este año tenemos el honor de contar con la presencia del profesor Jean-Philippe Steyer, director de investigación del Instituto Nacional de Agricultura, Alimentos y Ambiente de Francia, un referente mundial en su campo. Confío en que la cátedra Neal Amundson reunirá todos los atributos esperados y se cumplirán todos los objetivos trazados. Agradezco a las autoridades universitarias el apoyo brindado para el desarrollo de la cátedra Neal Amundson, al igual que el apoyo recibido por las diferentes dependencias del CUSEI, colegas y estudiantes del posgrado en procesos biotecnológicos e ingeniería química y servicio social que han hecho posible este evento. Les deseo a todos ustedes que sea de provecho en términos de su formación académica y se cumplan los objetivos trazados en la cátedra. Gracias por su atención.
A continuación, tendremos las palabras, un mensaje del profesor emérito, el maestro en ciencias, Héctor Antonio Rodríguez Sánchez, en conmemoración del 25º aniversario de la 25ª Cátedra Neal Amundson.
Buenas tardes a todos. Buenas tardes a todos. Además, quiero mencionar que el inicio de la cátedra Amundson se debió que en una ocasión hace varios años, el 19 de junio de 1984, se le otorgó el grado de doctor honoris causa al profesor Neal Amundson por su contribución a la educación de la ingeniería química. La noche anterior de la celebración, el profesor Amundson estuvo cenado con algunos maestros, Puig y un servidor, y ahí el doctor Puig le anunció que ya las autoridades universitarias se habían aprobado la fundación de la Cátedra Amundson, lo cual le dio mucho gusto a él. El día siguiente, en su discurso de agradecimiento de recibir el doctorado honoris causa, el profesor Amundson sacó un cheque de $15,000 para ayudar a fondear la Cátedra Amundson, que siempre ocupa de dinero. Entonces, $15,000 fueron realmente de gran ayuda y un gran apoyo de parte de él. Esa es lo que les quería contar, esa anécdota que se me hace muy interesante. Muchas gracias.
Muchas gracias. Muchas gracias. A continuación, tendremos las palabras de el doctor Humberto Gutiérrez Pulido, en representación de nuestro rector de centro, del doctor Marco Antonio Pérez Cisneros. Por favor.
Muy buenos días, tengan todas y todos ustedes. Es un gran privilegio estar esta mañana recibiendo a nuestro distinguido invitado, el doctor Steyer. Muchas gracias, doctor, por estar en la Universidad de Guadalajara, por estar en este centro universitario. Esta comunidad es una de las comunidades más vivas, más importantes de nuestro centro. Celebramos muchas cosas, 25 años de esta cátedra, así que lo celebramos con mucha alegría y de una gran manera con un experto internacional en la biotecnología, en los temas ambientales. Seguramente será muy interesante estos 2 días que estará con nosotros. Y decirle que este centro universitario es una de las comunidades más importantes de ciencias e ingenierías en el país. Aquí estudian 20,000 estudiantes y esta comunidad de ingeniería química, de biotecnología, pues ha sido una de las comunidades más activas, innovadoras e influido en las otras comunidades del centro. Así que muchas gracias por aceptar la invitación, por estar esta mañana con nosotros. Muchas gracias al maestro Antonio Rodríguez por estar con nosotros, por hacer el esfuerzo de regresar a su universidad, a su comunidad, de la cual usted sabe bien, es muy querido y respetado. Muchas gracias a los profesores, profesoras de esta comunidad y a los estudiantes que sin lugar a dudas tenemos el privilegio y la oportunidad de escuchar a una autoridad, como ya se ha dicho, en este campo. Agradecidos con su presencia y que sigan estando inquietos para visualizar primero cómo se ven ustedes en el ejercicio de su profesión, refrendar su compromiso en su formación académica, seguir siendo inquietos. Hay muchos problemas que esperan las soluciones de ustedes. Así que escuchen con mucha atención a nuestro invitado y finalmente una cátedra como esta es una oportunidad para profundizar en nuestro pensamiento crítico, en nuestra reflexión sobre los problemas que requieren una solución técnica. Muchas gracias al comité organizador, muchas gracias al doctor Norberto, al doctor Víctor Alcaraz, al doctor Pedro Ortega, que han estado atentos con la ejecución de esta cátedra. Bienvenidos a todos y pues de esta manera iniciamos con lo realmente importante, que es escuchar al doctor Steyer. Muchas gracias a todos y de esta manera iniciamos esta cátedra. Bienvenido y enhorabuena. El doctor Víctor Alcaraz, siempre cuidadoso de las formas, me pide que declaremos formalmente la apertura de la cátedra. Les voy a pedir se pongan de pie. Para, siendo las 11 horas con 22 minutos del día 22 de octubre de 2024, declarar formalmente aperturado la cátedra Amundson con nuestro invitado, el doctor Steyer, deseando que sea exitoso y reconfortante para todos. Muchas gracias. Buen día.
Muchas gracias, doctor Humberto Pulido. Muchas gracias, honorables miembros del Presidium. Antes de ceder la palabra al doctor Steyer, me voy a permitir leer una breve semblanza de su trayectoria académica. El doctor Jean-Philippe Steyer es un destacado investigador perteneciente al Laboratorio de Biotecnología del Medio Ambiente del Instituto Nacional Francés de Investigaciones Agronómicas en Francia, con una trayectoria sobresaliente en el campo de la ingeniería de procesos biotecnológicos, específicamente en la digestión anaerobia y la depuración biológica de aguas residuales. Obtuvo su doctorado en la Universidad Paul Sabatier de Toulouse, especializándose en la automatización aplicada a los procesos fermentativos. Su tesis fue galardonada con el Oscar de Valorización del Consejo Nacional Francés de Investigación Científica y reconocida como una de las mejores en automatique appliquée en 1992. Realizó su habilitación para dirigir investigaciones en la Universidad de Perpiñán, centrándose en el modelado y control de procesos biológicos para el tratamiento de aguas residuales. Sus intereses de investigación incluyen el modelado y la optimización de procesos biológicos para el tratamiento y la valorización de residuos y aguas residuales. Durante los últimos 10 años, los estudiantes de doctorado que ha supervisado se han ocupado del modelado de la diversidad microbiana, la integración de la termodinámica en modelos de balances de materia y energía, el desarrollo de modelos metabólicos, junto con innovadores sistemas de instrumentación en tiempo real para obtener una visión más cercana de la vida de los ecosistemas en bioprocesos y el análisis del ciclo de vida para tener en cuenta numerosos impactos ambientales. También ha ampliado su campo de aplicación con la digestión anaeróbica como bioproceso central, integrándola junto con procesos innovadores como el cultivo de microalgas para la producción sostenible de bioenergía y bioproductos. Ha participado en más de 9 proyectos de la Agencia Nacional de Investigación en Francia, como el proyecto RELOD entre 2021 y 2025 y el proyecto FICOVER entre 2014 y 2018, relacionado con microalgas y la captura de CO2 proveniente de la digestión anaerobia, contribuyendo así a la mitigación de gases de efecto invernadero y mejorando la eficiencia del tratamiento de aguas. También ha colaborado en más de 15 proyectos europeos y ha trabajado en colaboraciones internacionales con universidades e institutos de países como China, Italia, Bélgica, Israel, México y Canadá. Sus investigaciones y contribuciones a la ciencia y a la investigación en tales áreas, plasmadas en más de 360 artículos, lo han llevado a lograr un muy respetable índice H de 73, reconocido por Scopus, con más de 20,000 citas, y respectivamente un índice H de 91 en Google Scholar, con más de 31,000 citas. Cabe señalar que su contribución ha tenido un gran impacto en la ingeniería ecológica y los sistemas biológicos, destacándose como una figura clave en el desarrollo de estrategias innovadoras para el tratamiento de residuos orgánicos y la producción de energías renovables. Actualmente, el doctor Jean-Philippe Steyer también es actualmente el líder electo de la división Transform del INRA sobre ciencias para la ingeniería en alimentos, bioproductos y residuos, que recluta más de 580 puestos de tiempo completo en toda Francia y también es codirector del metaprograma del INRA sobre bioeconomía para áreas urbanas. Sin más, le cedo la palabra a nuestro distinguido invitado, el doctor Steyer, quien va a dictarnos la cátedra Anaerobic Digestion and All Story for Today and Tomorrow. Por favor.
Buenos días, todos, todos y todas. I'm sorry, that's my only Spanish I know, so I will switch to English if you don't mind. So, hello everyone. It's a great pleasure to be here, a great honor. I do thank you, Victor and Norberto, for the invitation and all the group. I'm very happy to be here today to tell you a little bit about something I've been working on for something like 30 years more on anaerobic digestion, and all story for today and tomorrow. So the first few words about my institute. So INRAE, it's a French National Research Institute on food, agriculture, food, and environment. It was founded in 1946 after the Second World War, to make France autonomous with food at the beginning. And so nowadays, we have big research challenges dedicated to ecological transition, sustainable production of healthy food for all, which is important for all, and also the use of bioresources and the bioeconomy, and also adaptive resource management and biodiversity. So we're quite a big institute. We are #1 in the world in agriculture, food, and environment altogether. You see some numbers here. About a little bit more than 10,000 people with 2,000 researchers, 3,000 engineers, and 2,800 PhD students and master students and postdoc. Quite a big budget. And also we are the first research institute to obtain the certification equality and diversity at work by European Union. We have today 5 scientific priorities. Today I will speak about the third one, which is about bioeconomy, and based on efficient use, circular use of resources, which is important. More than 200 laboratories in France, all over France, and we are one of them. So the Laboratoire of Environmental Biotechnology. We are located in a nice environment close to Spain, in the south of France. And this is the lab, like you can see in a big surrounding campus, like vineyards, mostly. We were founded in 1936. It was to develop wine. And this was a picture of the lab in 1936, inaugurated by Léon Blum, which was the president of France at that time. And we were working mainly on wine. Later on, we focus on wine wastewater treatment. And this is the first book. I'm sorry it's in French, but it's about vinasses of winery distilleries. It was written in 1936 by the founder of the lab, Michel Franzi. And just to tell you, it's in French, but if you translate it, it's written that by that time, wastewater and wine wastewater, so urban wastewater and wine wastewater, were rejected directly in the river that were passing by the Narbonne city. And it's written that the wine wastewater were worse than the urban wastewater for the fish and for the environment. So it was already in 1936 that researchers in my lab were thinking that treating wastewater could be efficient. So what I want to emphasize is linear vision is not enough. Linear vision was dealing with treatment of pollution. So you have wastewater, you want to treat it and reject it to the natural environment. Later on, you want to optimize this by recovering molecules, recovering energy, and to produce them in order to have more value to the treatment. And nowadays, what we do is we work in a circular way. So you want to use the cycle of carbon, nitrogen, and phosphorus, for example, but other materials, to maybe avoid treatment, but to emphasize valorization of this wastewater whenever it's possible. And since we deal with waste and wastewater, you have to account for sanitary, like pathogens, detergents, microplastic nowadays, PFAS, this kind of molecules, and you want to avoid that it goes back to the environment. Just an example of what is a linear vision. It's what we are facing today with agriculture. Basically, you first have the Haber-Bosch process, which produce fertilizers. I don't know if you have these numbers in mind, but Haber-Bosch process uses 2 liters of oil per kilogram of nitrogen, which is 1 to 2% of the energy of a developed country used just to produce fertilizers. Then you use these fertilizers in the soil to make products. 60% of this nitrogen is lost, which is quite a lot. 40% goes as a product to animal and human for feed and food. From this 40%, 12% is rejected in a wastewater. It goes to a wastewater treatment plant. Then you want to use, to transform this nitrogen into N2. And again, you use quite a lot of energy. 2% of the total energy consumed by a country like France, which is, you see, it's a lot of energy here and here, not too much being efficiently used and a lot being lost. So what we want to do is to deal with this and being more circular. So anaerobic digestion is one process, one biological process. It's natural process. It's the aim is to degrade organic matter. So you have organic matter, no oxygen, microorganism which produce methane and carbon dioxide and some residual organic matter at the end. This is our friends. So that's the bacteria that we use. And they have several advantages compared to physical or chemical processes. They occur in standard operating conditions, like pH neutral, temperature about 30 degrees, pressure, atmospheric pressure, no high pressure. People say there are some drawbacks. I'm used to say it's challenges because it's diverse. And microbial diversity is diverse, and then we'll talk more about this later on. Several years ago, we were to an international symposium with many kids, and we asked them, make a picture, draw a bacteria. And it was funny because half of them were drawing nice bacteria, but half of them were drawing bad bacteria. And bacteria are our friends. Just to illustrate, this is the number of microbes we have in our body. And if you compare the genes of our body, human genes, it's 23,000. If you compare these 23,000 to the genes of the microbes, you see it's just a little bit compared to the genes of the microbes. So if we live, if we can stand up, if we can get energy from food, it's because of the microbes. So now I will focus a little bit more on anaerobic digestion. So it focuses on carbon. So you have complex particulate waste, which can be degraded in carbohydrate, lipids, proteins, and some inert, either particulate or soluble. Then you have carbohydrates that is degraded in monosaccharides, proteins in amino acids, lipids in long-chain fatty acids, and carbohydrates in monosaccharides. Then you have acidogenesis, which converts these sugars into acids and hydrogen. Then you have the same for amino acid, the same from long-chain fatty acids. Then propionate is degraded into acetate and hydrogen, butyrate and valerate again. And finally, we have the archaea that will produce biogas either from acetate or either from hydrogen. So this is quite a complex microbial ecosystems, but you will see it's a very interesting ecosystem. The first thing is, it's Volta who make Volt, so discovered the Volt in 1966. And he discovered also the marsh gas, where when you mix the liquid, what is the bottom of the liquid, you produce something which can burn. As I said, it's a natural ecosystem. The ecosystem, it can be spontaneously produced in marshes, in rice paddies, in sediments, in soil, in our body. As you say, as we will discuss, rabbits are very efficient, cows also, and also this occurs in our colon, in our body. In terms of processes, it was first used in India, in Mumbai, to make light for a leprosarium. In London, in the late 90s, it was used to lit the city. Then you have a patent of the IMOF tank, which is this reactor, which make anaerobic digestion to develop. And this is in the 40s in France. This is a way to make gas to be used in this, to cook in the 40s in France. Today also in Brazil, you have a lot of wastewater, urban wastewater, which is treated by anaerobic digesters, USB. This is Belo Horizonte, 1.5 million equivalents, which is the wastewater is treated by anaerobic digestion. This is examples of processes you can see either in agriculture, in industries, but also like here in India and in China, at the local level, at the house level. And many of these are used in countries in Latin America, also in South America, in China and India, as I said. This is a process I worked with Victor several years ago. It's in tequila. And I mean, you don't see it in here, but the process is underground. Part of it is underground, because if not, it would have been higher than the church. And the church was supposed to be the highest point of Tequila City. So if not, it was the anaerobic digester that was treating the Souza tequila wastewater. So what to do with digestion? So treating waste from agriculture, from food industries, from cities, you produce a biogas, which can be used in a cogeneration to produce electricity and heat. More and more, you can also inject biogas directly in the grid, which can be used after as a biofuel. And the digestate, which is the remaining part, the liquid and solid part that is remaining, can be used as a fertilizer for soil amendments, for example. This is the situation in Europe. As you can see, an increase these last years, and I mean, this, I didn't have time to make new numbers, but it's still increasing nowadays all over Europe, mainly in Germany, but also in France and Italy and in Spain. This is the China daily. I was in China in 97, and I got this newspaper, and part of it inside was dedicated to biogas. And the conclusion of this, it's if you're a man and if you have an anaerobic digestion at home, you have a better chance to find a woman, which was maybe why this is 97, this is number of digester in China. It increased quite a lot. Compared to Europe, the main difference is here. In Europe, it was 1,000. In China, it's million of digesters that are operated mainly at the local level, at the house level, but also in big scale in China. This is the number of papers related to anaerobic digestion on the Web of Science. And you can see it's increasing quite a lot. I mean, that's where we started in our lab on anaerobic digestion. So nobody cared about anaerobic digestion by that time, and now it's more and more, which is good. Compared to aerobic wastewater treatment, if you take 100 of carbon, if you use aerobic process, what you mainly do is CO2. You produce CO2 and sludge. Sludge is bacteria that are growing using the carbon here and making CO2. So it's quite efficient. You remove 95% of the carbon, but you have to deal with quite a big number of sludge. With anaerobic treatment, so without any oxygen, you produce much less CO2. You make biogas and methane, which is useful as an energy source. You treat less, and also you produce less sludge. And if you produce less sludge, it means that also, which is an advantage, but it's also because it's slower compared to aerobic processes. And if you look at the classical wastewater in all over the world, what you do, it's basically you use aerobic process, activated sludge here, to remove carbon, nitrogen, and phosphorus. And what you do is you make sludge. And then you can make anaerobic digestion to process this sludge and to make biogas. With this scheme, the energetic balance is negative. So you consume energy quite a lot. Whereas if you change the process design, and if you want to recover as much as possible organic matter from what is coming and put upfront anaerobic digestion, then you can make energy out of this. So you can have an energetic balance at the same time treating wastewater and producing energy, which is interesting. So now I will tell you 3 stories. And first of all, about microbial diversity. I said it's a drawback, it's a challenge. Can it be an advantage? So this is a scheme of anaerobic digestion. And all of these arrows, you have bacteria involved. So what we did, we took 17 inocula, different, and I will discuss this later. We applied the same waste, and we wanted to evaluate the performance of this inocula over time. So what we used is as a waste was to make it stable, to have it stable and complex. It's a guinea pig food. And we put in reactors, so 17 reactors for 17 inocula for 6 months. And the inocula were coming from soil, compost, sediments, digesters. Some of them were used to make anaerobic digestion, but some others were not. That's a result after 3 weeks. So that's a different inocula, and that's a performance in terms of milliliter of biogas produced per day. You can see it's quite diverse. Some were very good, some were quite bad after 3 weeks. So if you leave them like this for a few months, few more weeks, that's what you get. So it seems to converge to one mean performance. But what is surprising here is these ones moved up in rank, like the number 23, which was very bad after 3 weeks. 23 is still here, but 27, where is 27? It's here. So it improved. The performance improved. What is also quite surprising, others, like this one in green, they move back. So they decrease their performance. So they were good, they became bad or average. So it was the first question we had. So why is this? So what we did is we continued the experiment, and for 3 months, we monitored quite well the processes, and we mixed all of them together. So 17 reactors, and in order to have a quite representative mixing of the different inocula, we ended up with 256 batch reactors to monitor at the same time, which if you run experiment, it's quite demanding. So 17 reactors, 257 reactors at the end, and that's what happened when you mix them. So without any bacteria, no biogas. Okay. This is the range of each of the 17 reactors, individual reactors you can have. And after we mix 2 by 2, 4 by 4, 8 by 8, etc., up to the 17 altogether. And what was surprising is you had an increase of performance and a decrease of the standard deviation, up to 27% more. What was also surprising is if you mix 4 reactors together after several months of operation, if you mix them, then the worst of the 4 reactors is better than the best of the individual reactors. So, and again, 8, it's even better than the best of the individual reactors. So the first thing is, well, if you mix 2 ecosystems, which different relationship between the bacteria, well, you can have nothing. You can have synergy in some part of the metabolic network, or one ecosystem can be emerged in the other one. And I mean, I will not tell you more about this. I will skip on something, but it's still an open question. And if you're interested to work on this kind of things, you can we can discuss this later. So this was interaction of the microbial ecosystem. What happens in terms of relationship between bacteria, one by one? So again, anaerobic digestion. So this is a fingerprint of the microbial diversity. One peak, it's one species, okay? So you can see the diversity. The thing is, if you apply a specific condition to the process, like a low pH, around 5.5, short hydraulic retention time, this bacteria, this archaea will be washed out. So you will not produce biogas as methane and CO2, but you will produce hydrogen and CO2. And the objective of this experiment were to produce hydrogen. So most of the time we ended up, after running this for several weeks and months, with one major species and several minor species. And I didn't understand what Victor said about me, but I'm a modeling person. And my theory says that if you apply the same condition, this one should be washed out, and they remain. So the question is, why do they remain? So we, again, several inocula from a digester, fermented manioc, feces of rabbits. As I said, rabbits are very good digesters. I will come back later. And a mix of all. And the inocula were easy raw, so diverse, or preheated 90 degrees for 20 minutes, which promotes the bacteria that are producing hydrogen. So you have less diversity if you heat compared to the raw. So you put this in reactors, continuous reactors, you feed them with glucose, which is a pure substrate, HRT of 10 hours, pH 5.5, you leave it for several weeks, so several tens of HRT. You end up with one major species, and several minor species. The thing is, well, 90% of the 80% in terms of weight is one bacteria, and the remaining 20% is completely different bacteria. So 80%, so you have the same performance, right? That's what we assumed. In fact, not at all. This is yield in red and productivity in blue. Well, what you can see, it's according to the inoculum, you can go from 1.2 to 2.4. So you can double the yield just because of them. So we investigated why are they here. And we started with one ecosystem with quite diverse, and we added Clostridium pastorianum, which is a bacteria which is producing hydrogen. So in terms of weight, if you make 50-50, well, you expect the mean of the two performances. So if you say 50 of this, 50 of this, you expect the mean, which is what you obtain. So, okay, this as a modeling person, I understand. But if you do the same and you change the bacteria, Ralstonia eutropha, which alone doesn't produce any hydrogen, well, you end up with more hydrogen. So this is something for me which was quite surprising. Another surprise was this is triplicates of one ecosystems. So you take 3 reactors, do the same. Well, in some conditions, in red, it's hydrogen production. You see it's varying. You also produce lactate, where in other replicate, you don't produce lactate. Whereas if you add this bacteria here, which doesn't seem to do anything, where you stabilize the hydrogen production and you stabilize also the product you obtain at the end of the fermentation. So we really spent quite some time to investigate the reason for this. And we ended up taking one bacteria, one Clostridium, which is producing hydrogen, with one bacteria which alone does not produce any hydrogen. So two bacteria. We mix them in a reactor, and so that's Clostridium and the sulfovibrio after some time. So you see that you have one peak. This is not as before, but it's the mass, I mean, the mean diameter of the bacteria. So you see that they are joining together. And what happens is, this is the results of Clostridium alone, okay? So it consumes glucose, produces butyrate, acetate, and lactate, and hydrogen and CO2. The same with desulfovibrio, which doesn't do anything, doesn't make any hydrogen. Well, what you do is you make more hydrogen, 2.5 more, and you make it faster after 20 hours compared to 25 hours. More and faster. And again, this bacteria, which doesn't seem to affect, if you make the metabolic analysis of the pathway, well, it has an impact of some specific routes. And we were wondering why. And on top of this, if you do the same as I showed you before, but you put one of them in a bag, in a reactor, so they can exchange liquid, but there is no contact between them, well, what you end up is the same as Clostridium alone and much lower than the two together, which means that you need a contact in order to be efficient. So that's what we finally found out. As a French guy, I say they need to kiss each other. And after it's very romantic because they live together and they die together. So it's romantic in bacteria, you can see. And you know, in order for this to happen, you need to stress them. You need to make an impact of make a perturbance on one of them, and after this, they kiss each other. Could we optimize even better this and take advantage of this knowledge to make better processes? So that's all the anaerobic digestion processes, the different technologies represented in terms of hydraulic retention time in days. So it could go to very short HRT to long HRT. And this is the concentration of solid in the feed. Here you have liquids, here you have pure, solids. So you have very efficient, high rate anaerobic digestion, solid phase leach bed, anaerobic lagoons here, and you have different technology. If you plot this technology with the efficiency of treatment with solid waste, that's what you get. Few kilogram COD, chemical oxygen demand, per cubic meter and per day. If you have a liquid, highly biodegradable wastewater, you can end up with 70 kilogram per cubic meter and per day. If you look at nature now, well, nature, the cow is 220 and the termite is 400 in terms of kilogram COD per cubic meter and per day. So our objective was to make a big termites, but mostly was to understand the reason why we go from this to this, because if we look at the digesters in terms of engineering, maybe you can reach 100, but if you think the same way as this guy, well, you will never reach 400, because my feeling is that nature, that's a sentence I saw somewhere, Mother Nature has found answer to question we don't even think of. So the objective was to try to find what was the question of the nature. So we said, okay, what we investigated, it's a digestive tract of different animals to understand if the performance comes from the food, the substrate, it comes from the design of the digester, or it comes from the operating conditions of the digester itself, assuming a digestive tract is a digester. If you look at digestive tracts in animals, in terms of reactors, you can have either a batch reactor, I'm sorry, still in French, continuous stir tank reactor, CSTRs in series, or plug flow reactors, okay? That's what you can get. If you combine this with a pretreatment is what happens, for example, in your stomach before, in terms of pH. So it could be acidic acid pH, neutral pH, or basic pH. And also, you can combine it with enzymatic pretreatment. Enzymatic coming from the body, enzyme coming from the body, or enzyme coming from the microbes in our digestive tract. So if you combine this with the technology, well, you have 24 possible configuration, okay? Guess how many nature you can find? Well, you end up with 8. So nature has optimized the digestive tract up to 8 different configurations. So first, as engineers, maybe you want to study this configuration, for example. Well, I would say it's not very good idea, because it's over the million of years of evolution, it didn't converge to this. So maybe you should focus on these configurations. Now, in terms of volume, okay, let's say you have carnivorous, omnivorous, and herbivorous animals. Let's say this is readily biodegradable substrate, slowly biodegradable substrate. Guess what? Well, this is the average process configuration of the digestive tract. Herbivores, you have a big tank up front with enzyme brought by the body, and then the plug flow reactor. Completely different configuration with carnivores. And in terms of volume, 80% here, 20% here, was for carnivores, it's 70% of volume at the end of the digestive tract. So, well, that's something. Why this? Well, I still don't know. But what I know, it's if you look at the herbivorous configuration, the cow, okay, llama, okay, oasin, I don't know if you know it, it's a bird which comes from which was already here when the dinosaurs were present. That's the configuration of the oasin. Oasin is the only bird which makes methane. Okay, so maybe the process configuration has an impact. Kangaroo, that's a digestive tract of a kangaroo. Well, you see, it's a different of them, and it doesn't produce any methane. So maybe the process design has an impact of the efficiency and of the final product you can get at the end. Last but not least, we also took feces from different animals. And we are lucky because we have a big zoo near our lab, so we didn't have to travel too far. This is the weight of the animals. And this is the microbial diversity of the microbes within the feces, assuming that what is in the feces is present in the digestive tract, okay? We didn't expect it at all, this curve. This is a logarithm index, and this is logarithm values. What you can see is, well, it's not perfect, but the bigger the animal, the more diverse the microbes in our digestive tract. There is an outlier here, the termite. If you remember, the termite was the best digester. But in fact, the termite, in order to process the organic matter, is raising fungi in a termite house, and the fungi degrades the organic matter, and then after the termite eat the fungi. So if you assume that the termite house has a digestive, you ended up here in this line. So the bigger, the more diverse. My conclusion also is, if you work at lab scale, like few liters, maybe you're not representative of what happens in the industrial scale. So you can go high in volume in terms of studying the diversity. Could we go further? Well, yes. This is the situation in France in terms of gas network, transporting gas. So you see you have big highways and you have small roads, okay? Similar to small roads. And what happens is normally you get gas, natural gas in port like this here, and you transport them different places in France, and after you distribute it, so you transport with the highway and you distribute with the small roads, the small pipes. Until recently, you can go from this to this, and you couldn't go back. You couldn't go from the local roads, the little pipes to the big pipes. Now it's possible, which has changed completely the situation. And moreover, that's a natural gas network, and that's an electrical network. What happens is that they can talk to each other, which is very important. Because if they can talk to each other, and if you have electricity coming from, let's say, import of electricity, nuclear power plant, coal, hydraulic, wind or photovoltaic sources, you cannot store, it's difficult to store electricity. But what you can do is if you have lots of sun, lots of wind, you have a high amount of electricity and you cannot store it, then you can convert it into methane with biomethanation. I will not go into details, but you can go to methane and inject it in the gas grid. In the gas grid, I don't know the situation in Mexico, but in France, 4 months can be stored of usage can be stored in a pipe in France. So you can store 4 months of energy just in a gas grid, whereas you cannot do it here. And so that's a way to combine electricity and gas to handle the fluctuation of electricity production from sun or from wind. And this, I mean, maybe, yeah, I know a story. You know, in Germany, by law, they have to take the renewable energy in their network. What happens if you have a lot of wind and a lot of sun, because they produce also from coal and electricity, they have an extra production of electricity. So what happens if they don't want the network to collapse? They need someone to take the electricity. So what they say is they pay for countries to take their extra electricity. So what happens is the Swiss, they are paid by the German to take the German electricity. They use it to put water in the mountain back in the lake. And after, when the price of electricity is very expensive, they open the valves to make electricity from the water, and they sell the electricity to the Italian, which are paying high price. Whereas in this case, well, you can have a local consumption of electricity without any economical problem. So that's what you can do. I told you before, we wanted to produce hydrogen, but also if you have an extra electricity, you can make water hydrolysis with physical-chemical process. You produce hydrogen, you inject it in the digester, and you make extra methane. Also, something which is important, methane is not only an energy source. Methane can be also used in chemistry and in green chemistry. And you can make a full spectra of different products with either syngas, hydrogen and carbon monoxide, or also methane itself that you can convert here into this, and then you make green chemistry based on methane. So this is a way to have an extra value of the waste, and at the same time, you remove the problem of sanitary constraints, because if you use biogas or methane, you don't have pathogens, you don't have detergents, you don't have chemicals, you just have gas. Also, to go even further, this is microbial bioelectro systems where you have 2 reactors connecting with a membrane. On one side, you put a cathode, on the other side, you put anodes. And what happens at the anodes, you have bacteria which can stick to the anode, transfer electrons. Ions will be exchanged through the membrane, and you can have different reactions here. And this reaction it's either direct electron transfer. I told you before, they can, remember the French kiss, they exchange proteins, they exchange molecules, but they also exchange and they communicate with electrons. So they exchange electrons here directly to the anode, or with different electroactive bacteria, or with different mediator, biological artificial electron mediator. So this is the different reaction you can have. And either you can make electricity because you transfer electron. If you make electricity, you can make electricity to charge your phone, but you will not make a train run, for example, because you're not able to make power enough based on this. But what is more interesting is you can make, if you apply differential of potential, so if you provide the bacteria electrons, you can make them produce different things, either energy, either CO2, either different processes, different molecules that are useful and that are made by bacteria. And last thing is, if you have a digester here, instead of going directly to hydrolysis and methanogenesis to make biogas, part of it, because it's a mixture, part of it you can use it in a bioelectrochemical system to make targeted molecules. And this is one way to have a biorefinery based on waste. So to conclude, this is my personal view of research. And that's why for the last 32 years, I'm still enjoying my job. That's my view of research. Well, what is the meaning of this? Well, if you see this, maybe you just stick on this. But if you go at the back, maybe you can imagine there is something. So imagine and think differently. Don't stay in front of the picture, go at the back. Dare to do it, because if you're in a museum and if you do this, well, maybe people will not be very happy. And last but not least, don't be afraid to be disappointed, because usually there's nothing, but sometimes it's very interesting what is at the back of the picture. So I thank you very much. I thank all my colleagues, because I was, of course, not the only one to work on this. And I have a special thank to a big friend of mine who is not here. Thank you very much.
Thank you very much, Jean-Philippe, for this interesting talk. Very, very interesting, and thank you. Thank you very much. We have time for some questions. We'll have one microphone on the auditorium, maybe.
Hi. First of all, thank you so much for the conference. I think it was very interesting. And my question is, what is the main disadvantage of the anaerobic digestion for making electricity or energy in general?
Main there is no disadvantage of doing it, because at the same time it's treating wastewater or waste and making a product of it, which can be energy. The thing is, it's slow, and people say anaerobic digestion is a difficult process to operate. I'm used to say it's susceptible, because you have a mixture of waste, and if you just bring it to the digester, you might affect the performance. So you need to control what you put in nicely, and in this case, you can make very efficient process. I will give a lecture tomorrow about this specific aspects of how to feed the digester the best way possible. So this is feasible, but imagine you take your garbage and you put it in a digester. Well, if you don't know what is inside, maybe you will affect the performance. So the main drawback is to handle waste, which can be produced at the, for example, at the agricultural level, according to the season, you don't have the same waste, the same quantity. So you have to manage all of this. That's the main disadvantage. I see.
Okay, thank you very much.
Thank you.
Good evening. First, I wanted to thank you for the conference. It was very interesting. I think it's going to be very useful for all of us. And my question is, one of the biggest challenges we have here in Mexico is the lack of environmental consciousness. So I wanted to ask you a recommendation that you have to all of us, to the companies, so we can improve this process. We can make that the country, well, or the companies can be more respectful for this technique, or that can make something more to use it.
Wow, that's a big question. First, we are free to buy what we want. So maybe you can put value to more than what you buy. So the way it is produced, the way it is distributed. So that's a personal view. I will not tell which brand, but I never go to one gas station in France because they are not very good in terms of environment. So that's one thing. The other thing is, I remember a few years ago, I said to my mother, "Hey, mommy, there is a nice show on TV about the environment. You should look at it." And she said, "Well, stop, please. I don't care about this." The same day, I was brushing my teeth with my boy, and I forgot to stop the water. And he said, "Dad, you have to stop the water." The message here is we should be aware, and I that you will be smarter than us dealing with environmental. But there is no unique solution. I mean, if I knew it, I would tell you and I would apply it, but I don't know it, unfortunately. But it's a question of what we do on our daily life, which can change the things. And if we don't buy products from a company, maybe they will change the way they produce it. Besides this, legislation, that's one point. But there is still a long way to go.
Thank you so much.
Well, thank you very much for your conference, Doctor. I have two quick questions. One is, when you talk about biodegradation of polymers, complex polymers, my question is, have you worked with typical condensation polymers or also polyolefins? And the polyolefins like polypropylene, polyethylene, etc. Okay, and the other question is, okay, do you foresee that we will be able to see in a few years more energy work with hydrogen, let's see, for society, more uses on hydrogen in a controlled manner? Thank you.
So in terms of polymers, microbes are quite good. Not all of them, not all the polymers, but the main problem I see it's usually they are mixed in small quantities with easier biodegradable waste. So the bacteria will not go for the polymers directly, they will go to the other ones. And so they will not degrade too much.
Yeah, we know that. I'm talking about examples of which polymers have you tried?
Oh, no, we don't work on specific polymers. We
typical
take-
condensation?
No, no,
No?
no. We
Which
don't,
polymers?
whatever is
Okay.
in the waste. So I mean, myself, I don't focus on a specific polymers.
Okay,
And,
okay, thank you.
and in
And the
terms
other
of
one?
energy, it's growing. The hydrogen, it's growing. Unfortunately, not produced by biological processes. It's more water hydrolysis of this kind of processes. At least in Europe, it was supposed to grow very fast. It didn't grow so fast. It was expected. But at the same time, what has changed a lot is the war in Ukraine, which changes completely the situation in terms of energy, gas itself. So now we are more concerned of not using natural gas, which was coming mainly from Russia, but using local produced gas, biogas mainly, not hydrogen. And so the French government said by 30, 40 something, there will be no more natural gas in the pipe. It will be only renewable gas. Part of it will be hydrogen maybe, the rest will be methane. So it's growing, but hydrogen, still some doubts about the evolution.
Okay, thank you.
Hi, first of all, thank you. It's nice having you here. My question is, what are the environmental impacts compared to other renewable energies? And how can it be implemented into life cycle, of, like the whole energy process?
Could you repeat it? With
Yeah. What are the environmental impacts of this processes, of this kind of processes, in terms of like greenhouse gas emissions and things like that?
In terms of greenhouse gas emission, what you have to be careful, I mean, it's good if the process is managed well, which is not always the case. For example, if you have a leak of biogas from the reactor, this can affect the life cycle analysis of the reactor itself. So you have to be careful with this. And also you have to be careful on how you use a digestate in the field. Because if you use it as a fertilizer, well, plants, they don't need fertilizer every day, every month in the year. But you produce it every day, you produce it every week, every month. So you need to store it and use it properly in the field. So the main point is leakage of biogas and the use of digestate, the liquid and solid part. Besides this, it's very good.
Thank you.
And there are papers on this if you're interested.
At the same, first for the conference, my question is there any risk at the moment you mix some microbes or any perturbance it could exist?
Is there any?
Like, is there any risk or perturbance at the moment you mix some microbes in the reactor?
Like any process, you have some risk. I didn't speak about it, but you can have foam. So foam being produced, and so you have a problem with overflowing of waste. You have problems also in terms of environmental risk. If you put too much digestate at one point, you will have leakage in the groundwater of nitrogen, for example. Um, but no, it's not really risky. I mean, if it's properly managed, again, biogas. If you have oxygen with biogas, you might run into trouble if you have a fire. It can explode. But I don't have any example in my mind that a digester has exploded. Never. Foaming would be the main risk, I would say.
Thank you.
And again, it's pressure, atmospheric pressure, normal conditions, so it's not very dangerous process itself.
Thank you very much, Mr. Do you see it profitable? Because you mentioned that we could use rabbit's waste also, which is a house pet. Will you see it profitable to like have a mini lab at home and process like more common house pets like dogs or ducks?
Do you see it profitable to have it at home? That's the question?
Yeah, like have a mini lab at home and process common pets waste. And because I know that you cannot do that on the countryside in the United States. I don't know in Europe. But for instance, here in Mexico, will you see it profitable to like make ourselves natural gas?
So you have many examples of anaerobic digestion being used at a local level, at a house level. I spoke about China, for example, but I have example in Venezuela, in Colombia, in different countries like this, where they use it to make heat, electricity, and local use at the house level. If you want to make money to inject biogas in the network, you need to clean it, and this is quite expensive. So it has to be quite big processes. But if you want to use it at home, it's possible. Yeah, and in Africa they use it also. I know examples also in United States, in big cities where they want to produce in buildings things to be used in the building. The main problem in cities is what do you do with the digestate? Because if you put 100 kilograms in a digester, you will end up with 50 kilograms. So what do you do with these 50 kilograms if you don't have fields where to spread it? But besides this, it's profitable. I have a colleague who is working a lot in Latin America to promote this. And the thing is, he installed more than 1,000 digesters in families' houses. The thing is, he stopped to make one digester for the house of the parents and the house of the children, which were close to each other, because when it doesn't work, the parents say it's the fault of the kids, and the kids say it's the fault of the parents, so they start to fight. So now they say one digester for one family and one house.
Okay, thank you.
Also one.
Thank you, Philip. I have a technical question. If I understood properly, the digestion process depends on the type of bacteria that you are dealing with. And you mix different type of bacteria to get some specific transformation, let's say, of this biomass. Is there any specific technique that you are following just to figure out which colony to pick up? Because I think it's a key issue to find out which ones combined can give you the transformation that you are looking for. Are you using a combinatorial chemistry? Are you using just trial and error? How do you figure out the colonies?
You know, depends what you want to do. If you want to make it efficient all year long, you know that the waste will be changing all year long.
Okay.
So if you want to make specific ecosystem with precise and defined diversity, well, it's like if you learn by heart a text, but you will know very well this text, but you will not be able to understand the other text. The same with bacteria. If you want to make it work all year long, what you're looking for is the most possible diversity. At the same time, what you want to do, and that's what is tricky, if you have a big change of waste, like a sudden abrupt change, then you want to know how to adapt to the waste the fastest possible. And in this case, mathematical modeling could be helpful, and that's the topic tomorrow. But mathematical modeling, it's difficult to handle the microbial diversity in mathematical models. So it's mainly try and errors, but also lots of expertise behind it. Yeah, I would say don't look for the most powerful microbial ecosystem for one topic if you want to deal with a huge range of waste. But if you want to, because the waste is changing even at industrial scale. So yes, so far I still try and error and expertise. There is no specific rule to improve a digester. But at the same time, when I spoke about Mother Nature, our microbial ecosystem is, well, it's adapted to, I'm used to the French food. I'm here, I'm drinking tequila, and I'm having tacos, which I'm not used to, and it's adapted. So, but how it is adapted, I don't know.
Well,
and I'm enjoying very much the Mexican food.
Thank you, Philip. Well, let me go back to the polymers. As you know, we are interested in removing microplastics and nanoplastics. And I believe one of the alternatives could be to use bacteria colonies that can metabolize these polymers. I wonder, you have found some colonies, so you have an alternative for doing that.
No, everyone would like to have it. People say bioplastics, for example. Bioplastics is not biodegradable, not always biodegradable. It can be non-biodegradable bioplastics. And bacteria, they don't know how to degrade this. They can store it, they can cut it, but to metabolize non-natural polymers, it's often quite difficult. And yeah, the solution would be to reduce the plastics or polymers usage. But yeah, and especially, I didn't see any successful process dealing with bacteria able to degrade this, for example. I don't know any.
Thank you, Philippe. Thank you very much.
I would like to, but I don't know.
Hi, well, thank you for your talk. I'm really nervous, so I'm gonna remain seated. Okay.
I'm nervous too.
Thank you. My question is regarding the cost of the implementation of this process in the industry. I had the opportunity to work at the industry, and I saw that they use the biogas from the anaerobic reactor. into the process mixed with natural gas. So I would like to know if it's more expensive, sorry, to clean the biogas rather than only use natural gas.
Um, well, it's not, I mean, it's expensive, but you have to make, you have to understand, you have companies that are using and selling natural gas. What they want to do is to sell their product. And at least in France, but I know other countries, the companies, they say, okay, biogas is dangerous. Biogas is explosive. Biogas is, it will carry microbes in the biogas that will cause problem in the pipes. So we had to demonstrate them that it was not the case. And at that one point, they were fixing the limit. To be able to inject biogas in the grid, it has to be 97% methane. 97% methane. Why was this chosen? Only because 96% at that time was economically feasible and profitable, but 97, it was not economically feasible, beneficial. So they fixed 97 just because to be quiet with their natural products. Now they change, and the biggest promoter of biogas in France is a natural gas company, because the government said by 2040, no more natural gas in the pipe. So you have to find something else. So now they're in favor. And so it's the technology to clean the biogas is expensive if the process is a low scale, small scale. In terms of kilowatts produced, it was 150 kilowatts. And if you go lower, you can make it, but it's more expensive. So you have a balance, and it's quite complex situation, but it's feasible.
And what would be like the number of companies in the European Union that are using this method? For example, would this be applicable in the Netherlands or in Germany, which are places very cold? And I don't know, in the Netherlands, they produce energy with the wind, with these things. So would they use this kind of system too?
Yeah. The biggest biogas producer in Europe is Germany. Then after it's Denmark, which is quite cold. In Denmark, I visited a digester, and the plant operator told me that he had pressure by the neighbors to make it work, because the neighbors in winter, they were using the heat produced by the digester to warm their house. So if it was not working, well, it was cold in the house. So he had pressure for them. So even in cold, I mean, surprisingly, in cold country in Europe, it's the most advanced countries with biogas. What happens is in Germany, for example, they make maize. They dedicate field to make maize, to make biogas out of it. Then you have a dilemma, because the field, you should make food for human, not maize for biogas. So that's why they changed now, but the many farmers in Germany were biogas producers, not maize producers anymore, because it was more profitable. In France, it's mostly the waste from agriculture, like manure, this kind of product. And what happens now is they discover, I mean, we know that it's beneficial for the environment to not have fields which are empty in winter. So we make intermediate culture that can be used for biogas during period where there is no food produced, and which is beneficial for the environment also. So it's a trade-off between energy, food, everything.
Merci.
Thank you. De nada.
Hello. First of all, thank you for the conference. It was really eye-opening. My question is related to the culture media. What are the limitations of mixing different types of bacteria when creating the formulation of the culture medium? Is there any substrate that inhibits one bacteria, or yeah, what are the challenges for that?
Well, in fact, many of them. Salt, if it's salty, it's difficult. Ammonia, if you have too much protein, it's difficult. So you have different things like this. What you have to be aware of also, it's how you feed the digester. If you feed it too much, it's like us. If you eat too much during lunch, then in the afternoon we will sleep. Well, the digester is the same. So you have too much will, I mean, you're not old enough to know Charlie Chaplin, Modern Times, you know. If you remember Charlie Chaplin with Modern Times, you have something passing by, and when it was slow, it could make it, but when it was too fast, it accumulates, and it was a big mess at the end. It's the same with digester. If you have hydrolysis, acidogenesis, acetogenesis, etc. These one are fast, these one are slow. So if you bring too much of this, you will accumulate this, and this will inhibit what is remaining. And it's like the snowball. You will accumulate even more, affect even more. So it's difficult. But besides this, I would say salt, pH, ammonia, toxic compound, but very specific toxic compounds from industry. But besides this, it's our body, our belly.
Thank you.
Thank you very much, Jean-Philippe, for this interesting talk. We are going to acknowledge once again, Martin, please. We're going to acknowledge once again Jean-Philippe Steyer for this interesting talk, and thank you again for being here. So,
La Universidad de Guadalajara, a través del Departamento de Ingeniería Química del Centro Universitario de Ciencias Exactas e Ingenierías, otorga el presente reconocimiento a Jean-Philippe Steyer por haber impartido la conferencia Anaerobic Digestion, a Knowledge Story for Today and Tomorrow for Some Remaining Scientific Challenges, dentro del marco de la Cátedra Neal R. Amundson, Guadalajara, Jalisco, 22 de octubre de 2024. Firma el doctor César Octavio Monzón, director de la División de Ingenierías, y un servidor jefe del Departamento de Ingeniería Química.
nuevamente, muchas gracias a todos. Un par de pequeños anuncios, los que gusten. A continuación vamos a pasar a tomarnos la foto oficial aquí en la zona de murales, y también tenemos preparado un pequeño brindis, bueno, un pequeño cóctel con algunos canapés y bebidas no alcohólicas aquí en el patio de Rectoría. Y nuevamente los invitamos para mañana. Tenemos la segunda plática del doctor Jean-Philippe Steyer. Déjenme recordar exactamente el nombre. Instrumentation, Modeling and Control for the Optimization of Anaerobic Digestion Processes. Y esta por mañana en el Antonio Rodríguez. Nuevamente, muchas gracias a ustedes, al comité organizador, y nuevamente muchas gracias a Jean-Philippe Steyer.
Vous me posez des questions?